Okay, we're going to try this again for the second time. Hopefully, this time this work. I'm doing this completely different. I'm actually doing it as a separate event because I set this up the day before. So if this is going to work, I'll know within about 10 seconds. And if it doesn't work, I'm probably going to start all over again like I just did. So for those of us, or for those of you joining us, we are doing Ask an Astrophysicist today. We got Dr. Jeff Zweerink from Reasons to Believe. We're going to be kind of discussing the difference between cosmology from a secular point of view as opposed to a reasons to believe type of approach. I do have his book here. Yes, I do. I've read pretty much most of it. I found it really interesting, so I'm going to try to dive into that right off the bat. But let me introduce our guest real quick. He's astrophysicist Jeff Zweerink. He's a research scholar and the executive director of the online learning at Reasons to Believe. He earned a PhD in astrophysics from Iowa State University. His writing and speaking encourages people to consider the connection between scripture's truth and scientific evidence. He is the author of Is There Life Out There? Who's Afraid of the Multiverse? And co-author of Impact Event Series. Jeff also holds a part-time research faculty position at UCLA. Oh, I didn't, I think I remember that. I actually got the chance to talk to you at AMP convention a couple months ago, and you're very kind. You spent about 30 minutes having a conversation with me, with Dr. Kenny Rhodes. And I was thrilled that I was talking to a real life astrophysicist because it's one of my favorite subjects. So welcome to my channel.
Thanks, Steve. It's good to be here. And astrophysics is one of my favorite topics too. So we share that.
I guess it would have to be, right? Can you imagine like not being interested in something like astrophysics and actually trying to do the math to it? I think you'd be bored out of your mind, right?
Yeah, that would be a tough way to live life. But I guess there are people who've done that. But that's part of why I got into it, is just because I enjoy it that much. So.
Yeah, see, I wanted to be an astrophysicist growing up, believe it or not. I loved reading about black hole theory and Paul Davies and Isaac Asimov and all the different back then what we consider to be cutting edge. But then I recognized the fact that my math skills were not up to par, and I probably never would have made it past quantum level mechanics and stuff like that. So I mean, I may still be a nuclear propulsion engineer with the Navy. I had to learn calculus, but it wasn't up to the level that you had. So anyways, listen,
the math is pretty challenging there after a while.
I'll tell you this before we get started. I have a dear friend, King Crocoduck. You may have heard of him. He actually is a YouTuber and a very well-known skeptic debunker. And he once showed me his homework when he was working on his master's thesis. I didn't recognize it as math. And I thought I've seen a lot of types of math. This was bizarre. It was, you've seen orbital mechanics, right? And all that kind of stuff. It was like that on steroids.
Okay.
So
yep.
It was very bizarre. And by the way, you recognize the fact I just shaved. Yes, the people on my channel that have not been here the last day or so, I did shave. There's a couple of reasons why. I'm going to start getting a tan. And if I just let it grow back, then, well, we'll worry about it then. So anyways, let's kind of dive into this. First, before we get into your book, do you want to kind of briefly explain RTB cosmology in a nutshell? And then we can kind of maybe give the distinctions between that and a secular viewpoint?
I was thinking about that. When I saw that title on there, I thought, well, that's kind of an interesting way to look at it. And if I'm honest, the way I look at it is that you go out and you do cosmology. And I think a Christian can do cosmology. I think a Buddhist, a skeptic, anybody can do cosmology, because what you're doing is trying to go out and say, all right, what's the best explanation for the mechanics of the universe and how it behaves? And then I think where I would say the Christian part, or the RTB part, comes in is not so much do we do the science differently, is like, okay, now let's take a step back and say, given what we found, does that support a particular worldview or not? And I also think it does work the other direction as well, that as a Christian, I could say, okay, the Bible talks about the universe having a beginning. So obviously, when you're dealing with cosmology, that plays in there. How would that play out in terms of what I look for, what I see, what I'm going to find when I do that? And how would I make any sort of measurement or scientific advances that would illustrate or illuminate whether there's a beginning or not? So I don't want to communicate that, okay, as a Christian, I come at this and I do the science very different than a skeptic or a Buddhist or somebody else would. It's that there's a place to where I'm going to step back and say, as a Christian, I think there are some things that are true of the world that, if that's true, I would expect the science to show or to reveal that or to support that at some level. And I'm going to be willing to, or I'm going to step back at some point in time and say, given what we found, does this support a Christian worldview or not? So that's kind of my perspective on how I do cosmology, if you will.
Yeah, and I don't think that differs a lot from the secular way of doing it. Science is very similar. Some people made the argument that science affirms the consequent. Now, I don't think that's actually true. I think it's more of a modus tollens thing. I think that now it's nice to go out and say we have hypothesis, go look for evidence for it. But I think a lot of scientists will more go along the lines of saying, hey, I have an idea, I have a hypothesis, let's try to falsify it and see if they can or cannot. So when you say something like the beginning of the universe, which is very prevalent, you find in like the Kalam cosmological argument, there's a lot to be unpacked there. People don't seem to recognize that there's a lot of issues with beginning. And I did a presentation on the no boundary proposal, which was something that Hawking had put forth using negative time to kind of get back to t equals 0. Would that be something that would be what you could consider the beginning point? If the universe had a beginning, would you use something like that to say this is the point? Even if hypothetically, going to your book here, there was something like a multiverse. I'm not talking level 1. I do accept level 1. Well, level 2 and 3, maybe not. I don't know. It's a little more complex.
That's actually a great question, and one that I don't have a definitive answer for, because I guess my original introduction to cosmology and science apologetics for Christianity, if you will, is, you got the space-time theorems of general relativity, and this shows that there's a beginning to the universe. And so I kind of accepted that. At some point in time, I had to go in and look and say, all right, well, what did it actually show there? Or what was the result that people looked at and said, okay, that means there's a beginning? Because I'm pretty convinced out there's no stopwatch, that all we have to do is find that stopwatch and say, there's the beginning, So the question is, what scientifically would we measure that says there's a beginning? Well, with the space-time theorems of general relativity, it was a statement that if general relativity describes the dynamics of the universe, as you run time backwards, eventually you run into a boundary where the laws of physics break down. And so where the laws of physics break down, that singularity would be consistent with the beginning. And so that was where it was. So, there's obviously two ways you can go, or there's more, or at least two ways you can go with that. One is you can say, okay, there's a singularity that implies a beginning. Or there's another, in some sense, equally good approach is saying, okay, there's a singularity. That's a sign that we don't understand what's going on. But, so that was one place where people came along and said, okay, that would be consistent with the beginning. But so the question in my mind is, as a scientist, as I'm going and looking, what would be evidence of a beginning, or what would point towards a beginning? And there's even within that question, what do you mean by a beginning? Because I think there's kind of a phenomenological beginning that you could talk about to our universe, which, say a level 1 multiverse where inflation ends in this region, and for all intents and purposes, all we can measure is what's within this region. And that had a definitive time to it, if you will. I think that's one way you could talk about a beginning. And then, I guess from a scriptural or from a Christian standpoint, I think there's actually a more fundamental beginning, that there's the beginning of all physical existence, if you will. That, that seems to be what the Bible's talking about, that there's God created things out of nothing, if you will, not just refashioning pre-existing stuff, but there is some sort of ultimate beginning, or I'm not quite sure the right term to use for that. But so in that, the questions or how science would play in that is kind of varied, and part of the challenge of this is that we're dealing at the frontiers of our scientific knowledge, where experimental data is hard to come by one way or the other for this. And so it's one of those things that makes it kind of a fun area to play around in, kind of in some sense, regardless of your worldview perspective, if you will.
Yeah, and I did like the way you put it in the book. You weren't heavy-handed on it. You basically put it forth as, why should any Christian be afraid of the multiverse, right? It shouldn't be something that you as Christians or anybody should really be worried about one way or another. It's interesting, and I do agree with you, according to your book, that a multi-level one universe, being a Hubble sphere, right, just a Hubble's volume, that makes sense to me, right? I think that there is that level of multiverse. Now, if there was a higher level of multiverse, where if you want to explain to the people like a level 2 opposed to level 4, and then you get all crazy with a level 4, which is basically a string theory with 10 dimensions. If I have to go all crazy, because in string theory with multiple dimensions, you're allowed to have pretty much anything. And that's the way I'm kind of reading the 4th level of multiverses. Anything is kind of possible. But
Actually, the level 4 multiverse is even more bizarre than that, because the level 2 multiverse would be or 2 and 3 would be the string theory type versions.
Oh man, yeah, because I was looking at the level 2 is just basically individual pocket universes that are kind of in some kind of nucleation of a bigger type structure of some sort. And so if that was the case, then there would be no way to actually have any kind of interaction between one universe and another. There'd be literally no causations between the two. Nothing could ever travel between one and the other. Okay, so they're fundamentally isolated from each other.
For all practical purposes. I mean, there's obviously little places, right, when they're forming, can they collide and things like that. But for all intents and purposes, once they're formed, the region between those grows larger than time could have, or anything could travel across that region. And so they effectively become isolated after they're formed.
Okay, we'll say they're spatial temporal, I guess, isolated. Okay.
Yeah.
So if for example, that if a God does exist in some capacity, I think that you would agree that if the universe, our universe, is around 13.8 billion years old, and it had some kind of beginning, I'm okay with that. Right. One way or another, it doesn't really factor into my ontology. But there is something prior to that that's not considered to be our time. Let's call that multiverse time. And again, I'm probably making up terms, but I'm just trying to relate it in a way people can understand it. A multiverse time, which is completely outside of our own space-time four-dimensional continuum. So if God at some point was this infinite being, and he had to create our universe temporally, we'll say in B theory of time, where did this kind of take place? Or did he create like the entire multiverse? And then there was this kind of chugging around in his own time. And all of a sudden we've kind of sprung into existence at a certain point on that temporal mega time structure, in which case it seems to be a lot of excess energy that God used in order to create all this, where nothing was actually happening that we were privy to, and we could never be privy to, right? Because we can never get to a second or third level or fourth level. So what good are they if we can't even know they even exist?
Well, but that, I mean, you know, before getting it to the actual, or how the beginning and time plays out there, that problem of there's stuff out there that we can't ever get to, won't even know exists, that's true even on a level 1 multiverse.
Fair enough.
Yeah, there's just a whole bunch of stuff out there. And so you can say, you know, is God wasting time or energy? And kind of a reasonable question, but at some level, God is an infinite, you know, I mean, as a Christian, I would say God didn't exert any energy or, you know, get tired or worn down or anything. So whether he creates one planet that can house life or a multiverse with billions of galaxies in there or billions of universes, that's kind of neither here nor there.
He wouldn't be expending anything extra to do it. If he, I'm gonna grant he's an omnipotent being if he exists. Yeah. Before to him, creating one sand or quadrillions of sands or stars is the same amount of energy to him, I would imagine.
Right. Yeah.
Okay. So I'm cool with that. It's just that if these structures are forever outside of our observation, now the level 1 universe, I might try to argue that there is theoretically a possibility to go beyond that boundary. Maybe. Okay. If, for example, there was a way that the universe would stop expanding and start contracting again, maybe would that be possible?
There's a lot of possibilities. I mean, you know, that's kind of where the challenge is, you know, how do we figure out? We could put together a lot of things that might exist, but testing that scientifically is a little bit of a challenge.
Right.
So, you know, that's one of the issues we have is trying to figure out what's going on with all of that. And how do we test one way or the other? Which one's going to be the working there? So, so all that to say is, I think regardless of whether you go with a level 1 multiverse or with a level 2 or 3, you're dealing with stuff beyond what we're ever going to come in contact with. So, but that really, in some sense, doesn't bother me. I guess the bigger question, you know, and you kind of alluded to it, or what you were addressing there in the first part is, how does this play in with the beginning? You know, I mean, I think you could say clearly there's some sort of Big Bang beginning to our universe, even in the level 2 multiverse. But there's a question of, you know, so I guess let me take a step back and just kind of describe the level 2 multiverse so that we see where this question comes in. Because if you just take I
got pictures.
Sweet. Yeah, there
cool?
we go.
We like to have diagrams here because, you know, our audience, they usually are used to pick. All they have is like picture books, the pop-up books.
Okay.
Okay.
All right. All right.
And I just lost like half my audience. Thank God.
Oh no.
Okay. All right. No, go ahead. So that's what we're looking at.
I like that picture, and the idea is just this: that if you go with, and I'm going to give a little bit of history to know why the idea is motivated, is that you've got this idea of an expanding universe governed by general relativity. So you got expansion, and then you start asking these questions of why is everything the same temperature no matter where we look in the universe, and why is the universe so flat from a geometry type standpoint? And really, what was a more sort of bizarre, mundane question, or bizarre question, is why don't we have any magnetic monopoles? And there are physics reasons why we would expect things to be different than that. But as people were exploring what's going on in the earliest moments of the universe, scientists had this idea that all the fundamental forces unify into a common theoretical framework, which we're going to call the theory of everything, is kind of the terminology for it. And so when you go in and you unify electromagnetism and the weak nuclear force, there are some consequences to that we can measure in our universe. And one of them is there are these W and Z bosons. And lo and behold, we went in our particle accelerators and found those and said, that's a good way to pursue. Now, as you go and try and unify the strong nuclear force with the electroweak force, one of the consequences of that is that you get all these magnetic monopoles. And so one fellow in particular, I mean, a lot of people were working on that, but Alan Guth was looking at why are there no magnetic monopoles in the universe? And what he realized is that you could have these, depending on how you do that unification, you can actually get the universe to be expanding very rapidly, and that will dilute all the magnetic monopoles. And so, yes, those magnetic monopoles are formed when the strong nuclear action separates as the universe cools down. But you've got this hyper fast expansion that dilutes all the magnetic monopoles out of existence for all practical purposes, so we never measure them. And as they began to look at it, they realized, hey, that also explains why the temperature is so uniform in the cosmic microwave background radiation, and why the geometry of our universe is so close to flat, even though we couldn't find enough matter to make it flat. And so that's kind of where you get this Big Bang cosmology with inflation thrown in on top of it, because that seems to provide a good explanation for most of our observations. Well, now scientists begin asking the question, how do we make inflation work? And you can have things that are at higher potential and they decay to a lower potential, and that's what's presumably going on in inflation. Well, inflation works in such a way that when it's at this higher potential, space just wants to get larger, and the larger it gets, the faster it wants to get larger. And so that's a great mechanism to drive this inflationary phase. But then you have to get it to decay and give a more ordinary universe like we have. And the thought was at the time was that you'd have this inflation potential decay to a lower energy state, and it'd do that all sorts of different places. And then those regions where it had decayed would grow, and they'd join up and make the uniform background like we see in the cosmic microwave background. But they eventually showed that that cannot happen, because while it's the places that have decayed, in between are places where it's undecayed, and those are expanding very rapidly. And so that's where Guth and others came up with this idea. What happens if where it decays, our universe is inside one of those regions? And so now you can kind of see where that level 2 multiverse comes.
Like a bubble, a nucleation
right, one of the bubbles inside.
Yeah. And by the way, I should have asked if I can show your pictures because it's your book. Is that okay?
Oh, yeah, that's fine.
Okay.
That's fine.
Yeah. Matter of fact, I actually was able to talk to Dr. Krauss about Alan Guth and the no free lunch that he came up with. Right. It's basically this net zero summation of energy from nothing. Basically, something from nothing in some ways, even though it was if you do the summation, it actually goes to zero. But for my audience here, the inflationary period of the Big Bang was, as you said, to try to really solve 3 major issues. It was one, the missing monopoles, the flatness problem, and then the cosmic horizon problem, which if people would understand this, if you have a big, large universe, right, then 2 points of opposite space will never be in causal contact with each other. They should not be in thermal equilibrium, right? And we looked at the cosmic background radiation, and we found it was very small delta. It was still around minus 270. how much was it? What two?
Okay, so it's about 2.72 or 2.3, well, about 3 Kelvin right now.
Oh, 3 Kelvin. Okay, 2.7, 2.3 Kelvin. But it was a very small range of fluctuations, right?
Right.
And these fluctuations are explained from the fact that the way I look at this, hopefully I got this correct from talking to Dr. Krauss, is that they're actually like a snapshot of the quantum fluctuations at the inflationary period. And so what we're seeing is basically literally the nucleation points from that quantum fluctuations spread out, and those are what giving us the distinct difference in the temperature, and that's why doesn't have this homogeneous effect. It doesn't have this. It has always called anisotropies, right?
Well, so it is incredibly anisotropic.
Yeah.
When you look across the sky, but when you look at fluctuations now on the part of 1 part in 100,000, you now see these fluctuations, and that's those, and for the W map, it's the red or the green, blue, and red map. For the Planck, it's kind of that blue and red, orange map. Those fluctuations are what allow galaxies and clusters of galaxies and stuff to grow. Those provide the temperature or the density wells that allow those large structures to form.
Is this like a supervenience thing, though?
What's that?
Is somewhat like is it like a supervenience that these small changes that happen very, very early on are now having these extra long, big scale changes? Are we seeing the fact that we're having, for example, look like the what is it called? The Hercules Great Wall in Hercules. Okay, so that's one of the biggest. That actually, I think, is the biggest structure in the observable universe, at least as far as we know. Is something like that caused by the fact that these quantum fluctuations happened at the beginning of the inflationary period, and so it's causing what we see to have these weird structures out there, or is that just completely related to gravity?
It's both.
Okay.
So in order for things to, if everything's perfectly homogeneous, then no structures are going to form because gravitationally nothing's going to clump up. And so, what happens in the early moments of the, those quantum fluctuations that get encoded, you've got some density fluctuations that even before protons and electrons and neutrons can start clumping, because the universe has to cool to a certain temperature before that can happen effectively, you can get these gravity wells because of those quantum fluctuations. And so you can think of, higher and lower temperatures or translate largely into gravitational wells, gravitational voids and gravitational wells. And so, those quantum fluctuations play a role play a very critical role in gravity allowing structures to grow as large as they do, as quickly as they do. Because if you just have, normal matter and no quantum fluctuations, that really can't start clumping together until something akin to, where the cosmic microwave background radiation is released. Because that's, matter is pretty much homogeneously distributed at that point in time. But the dark matter doesn't interact much with electromagnetic radiation, and so it can clump sooner. And these fluctuations in the density from the quantum fluctuations allow that to even happen faster. And so that all is part of that picture, that you start from the quantum fluctuations at the end of inflation that are amplified to large scales that now allow dark matter to clump up. And as the universe grows, now gravity grows these incredibly large structures that we call superstructures and walls and clusters of galaxies, and eventually galaxies, planets, and us being here. So actually, gravity doesn't grow us here, but it allows the place where we live. So
gravity may not be the strongest force, but it's the furthest force. It's infinite, so it basically affects everything.
Electromagnetic is also infinite. Gravity is the only one with no counter to it. So with gravity is always attractive, where electromagnetic, even though it's infinite, can be attractive and repulsive.
Well, there is negative gravity, isn't there? Though
not in the same way the electromagnetic, because you can have a positive and a negative charge that can attract each other. You don't have a positive and a negative mass that will attract each other. So that's why on the large scales, gravity always wins.
Right. Yeah, it's the dominant force. Right. I'm going to start opening up to Q&A in a second, but just to explain to the audience out there, because it's one of my favorite things, the cosmic background radiation is basically, the way I understand it, is caused from the fact that after the inflationary period, there was the recombination period, where basically you had a sea of highly dense plasma, I guess, because it wasn't stable atoms yet, and so you had electrons not bound to protons yet. And so photons that were bouncing around there had this opacity. They couldn't go anywhere. They were basically encapsulated in this hot, dense plasmic soup, I guess. And as soon as it cooled down enough where the electrons could combine with the protons, forming monatomic hydrogen, then that sudden collapsing caused all those photons in there to be released. And that bright flash of light is what we're seeing now as the remnant, what we call the cosmic microwave background radiation. Would that be a decent way of putting it?
Yeah. So it's, helium or hydrogen atoms form around 300 or 3000 Kelvin. And so as the universe above that temperature, anytime an electron would join with a proton to form an atom, the photons were just energetic enough that it would knock it back off. And so you had this kind of equilibrium. But now you drop below about 3000 Kelvin, the protons and the electrons join and you get hydrogen. And now when they join, they give off a photon, and that streams now freely through space. And so, yes, we see, and that temperature changed largely uniformly at the same time throughout the universe. And that's why we see the same temperature everywhere throughout the universe.
That's why there's some homogeneity there.
Right.
That's awesome. All right. I have put the link to join in the video chat. I'm only allowing certain people that I kind of know, obviously, to come in. And all you have to do is click that in any kind of browser, and it'll take you there via Zoom. It's easier if you download Zoom, and I do recommend downloading Zoom. It's a heck of a lot easier than Google Hangouts. But if you don't have that ability, just click on that link, and it should take you to a web page. Then you join, it'll ask for some information, then you'll be able to come in and ask our guests some questions. If you also want to ask them in the live chat, please, by all means, do so. Somebody had asked this, and I did see one. It looked like a decent question. Let's see. Alan says, is a quantum fluctuation that the fluctuation arises from if one-to-one geometrically with space-time filling all of space, inherently a block time producing emergence? I don't even know what that means. I don't know if you do either, because Alan, I like Alan. I never understand what he says half the time. And I don't know if it's just my, something in my epistemic limitations, or maybe he needs to rephrase that a little bit differently.
Yeah, I guess
block time produce. I know what block time is. I mean, that's something that block time is. What do they call that model? It's a cubic time where, what do they call that? When you have like the growing. Somebody help me out here, guys. I'm dying here. The growing cube model. Have you ever heard of that? It's like when you have blocks of time growing instead of having A/B time.
Oh, yeah, I've looked into that a little bit. It's like that there's this. Well, I'm not going to venture into that because I'll probably say it wrongly if I do.
I think it's called the growing block universe.
Okay.
Yeah. So according to
I don't know that it relates to that. I just know that we can make these measurements, and we know this is going on. So if you take a volume of space and evacuate everything out of it, the fabric of space will fluctuate antiparticles into existence.
Mm-hmm.
And we can measure that in the lab, because you can actually make measurements that if you put plates close enough together, there's only certain kinds of fluctuations, and you can measure a pressure.
Casimir effect.
There's more, the Casimir effect, right? So space just fluctuates these particle-antiparticle pairs into existence. All that's going on in inflation is that instead of those particles being able to fluctuate in and out of existence, inflation is when they fluctuate into existence, they're blown up onto really large scales before they can reannihilate.
So it's
just those fluctuations.
So it's kind of like, okay, let's say you look at Hawking radiation, where you have a boundary condition on the event horizon of a black hole, and you have a particle duality being created. You got a particle that actually has to go into the event horizon. The other one gets ejected as a real particle with real momentum, real mass. That causes evaporation of the black hole.
Right.
Hawking radiation would predict. So you're saying something along the lines of, if you have a rapid inflation during that time of pair production, that you can split them and one particle becomes real? Is that how it would work? Yeah,
basically, it's like they would normally fluctuate into and out of existence, except that when they fluctuate in, the space just grows before they can reannihilate. So they effectively become both real particles. So
see, I'm fascinated by that before we get our caller in here. Because when I look at a Feynman diagram, right, Feynman has a unique way of looking at particle-antiparticle creation. He has one particle moving forwards in time, and he has one particle moving backwards in time.
Right.
So if you have space-time inflating, how does that work if you have one particle moving forward and one more particle moving backwards?
Well, so there you get into a problem. The short answer is I don't know how to answer it within what Feynman is saying, except I will say this, is that there are lots of different ways you can envision reality working and then say, okay, how does that work out in terms of what I'm calculating here with quantum mechanics?
Okay.
And so you can take or Feynman's interpretation or Bohm's or you know, all of these different interpretations. And the reality is that they all basically give you the same predictions for the experiments, but they all interpret what's going on very differently.
Like Copenhagen versus pilot wave theory or Bohm.
For example, yes.
Okay.
And so to me, that says we don't really understand fundamentally what's going on there. So it might be, you know, Feynman has enabled us to calculate things graphically and, you know, kind of have a good picture of it, so it facilitates doing the calculations well, but his mechanism may not be based in reality at all. So I don't know what you would be saying exactly there. So
yeah, I think I read the same thing, because the way I look at pilot wave theory just seems to be it works, but it adds a lot more assumptions, I guess. But anyways, Alan. Oh no, we can't hear you, Alan. We're so close, man. We're so close to hearing you, but no, not working. Nope. Okay. Well, we're waiting for you, Tom, a person who actually is in-depth understanding of quantum mechanics. My friend Tom. Do you have a question for our guest?
Yeah, I have one question. I have two questions. I asked this. Maybe you will remember, Steve. One is, as I understand, the Hawking radiation at black holes is kind of explained by a particle and an antiparticle is forming exactly at the edge of the black hole, and the particle is flying away from the black hole and the antiparticle is flying inside of the black hole, and therefore the black hole is losing mass. But what I don't understand, if this is a process that is sort of randomly with no preferred direction happening, shouldn't it cancel itself out? Like there would be particles flying outside of the black holes and antiparticles flying inside, and vice versa.
So as I understand it, it doesn't really have to do with whether it's the particle or the antiparticle that goes in. It's just so you look at the black hole kind of as a static entity. If you know, so let's just look at that picture. So you got on the boundary, you've got a particle-antiparticle pair that gets created, and if one of those falls into the black hole, it's now constrained and confined to the black hole. But you have the other particle flying away. So conservation of mass, if one of the particles flying away, that means the black hole has to lose energy, is what it amounts to. And so it doesn't really matter whether it's the particle or the antiparticle, because they both have the same mass. But over time, the black hole gets less massive because some of, you know, where those particle pairs, one falls in, one flies away, for that one to fly away, the black hole has to get lighter.
Oh, I see. I thought it would always have to be the particle flying out and the antiparticle.
I guess it really doesn't matter. It's just half that particle. It doesn't matter what thing. Half of it has to be ejected, and the other half has to go in, and that's going to part.
Exactly. You know, because if you take an electron and a positron has a mass of 511 keV, and the electron has the exact same mass. So it doesn't matter which one flies away, you've extracted mass out of the black hole.
Now, why is it just for why is it just like virtual, like photons or virtual electrons? Why is it not virtual quarks? What if they're not unbound? If they're, let's say you can have unbounded quarks. How do you know? There's a superparticles that can be created and destroyed so quickly that we don't even know they're there. So with these virtual particles, are they actually what we consider to be photons or electrons, or they're just nothing until they're actually something that comes out of it, and then they manifest in some type of particle?
Well, that's just it, is that until, you know, while they're just fluctuating in and out of existence, the property of space that allows them to fluctuate in and out of existence, they're described by the fabric of space itself. So now, you know, and the, you know, Heisenberg's uncertainty principle, you can have anything fluctuate into existence, but you're going to have a change in energy to do that. So that constrains how long they can do that before they have to annihilate again.
That's an energy time uncertainty.
Yeah, the product of the uncertainty and the energy and the uncertainty and the time must be smaller than a certain amount. So if now you take a black hole that can extract, or, you know, can separate those, that now is no longer, we're not no longer dealing with the property of the fabric of space. We've taken, and I don't know the exact mechanism or the details of how this works, but effectively what you've done is taken some of the energy of the space-time fabric and made a real particle out of it. You extract that energy from the mass of the black hole to make it work.
That makes sense, Tom? It's basically, Heisenberg's uncertainty principle would be that you can never know the exact momentum or position of a particle at the same time. But it also, you cannot know the exact energy and time of a particle as well. Is that it? The delta E, delta T, if I remember correctly?
Correct.
Okay.
And this is
I'm really pulling this out of my head here, trust me.
And this is the sort of process we actually use to explain, so we were talking about the range of the forces. The reason why, the interactions is probably a better term. So the strong and the weak and electromagnetic interactions, the reason why they have the range they do is because of the particles they're mediated by. Gravitons and photons, which mediate the electromagnetic and gravitational force, are massless. So there's no limit to how far or how long those particles can come into existence. Whereas for the weak nuclear force, they're mediated by bosons that have masses, I think they're around 80 GeV, somewhere in that range. So
intermediate vector bosons.
Right, exactly. So to fluctuate something like that into existence, it has to go back out in a very short period of time. It can't fly very far. That's why they're very short-range forces. So this isn't just some fancy mathematics we've come up. It actually describes a lot of very fundamental interactions and measurements we've made in the labs.
And that would be the same reason why, for example, in the nucleon itself, you have three quarks, whether you have two up, one down, or two down, one up for a neutron and proton. When they're in that bounded state in an atomic nucleus, the secondary effect of the strong nuclear force between the binding of the quarks by gluons will extend just far enough past the boundary condition of the proton or neutrons to bind the nucleus together. It's a secondary effect of the strong nuclear force. So is it because the gluons are the certain size and certain energy that they have, that boundary condition for which they can only be a certain size nucleon or a nucleus? I think it's like maybe 134, I think is the Z number. I'm trying to remember whatever it is.
So there's another thing that comes into play there is that with the gluons and the quarks, their behavior is very different. So if I take two protons, ask how much, or let's say, we'll just go with two protons. If I ask the question, how does the strength of the interaction from an electromagnetic interaction vary as I move them apart? The more I move them apart, the weaker the interaction is between them. That's true for the weak, is true for gravity for sure. Now with the strong nuclear force, so when I've got two quarks, the further I move them away, the stronger the interaction gets between them. And so if I move two quarks very far apart, what's actually going to happen is that the energy density in between them gets so large that it's more advantageous to create a particle-antiparticle pair that now connect, so that I've got two quarks over here and two quarks over here. And so that's why, this whole process plays into why do nucleons behave the way they do, because there's not just a couple of quarks. It's very complicated inside.
I've looked at a diagram of the virtual quarks that would exist.
Yeah.
It's basically very similar to the orbitals of electrons. There's a probability of where that quark will exist in that nucleon.
But it's even more complicated than that. We can talk about a proton being two ups and a down, and a neutron being two downs and an up, or I might have that switched around. But it's not just three quarks in there. There's a whole sea of quarks,
right? It's a particles
in there,
right.
And these are kind of valence particles, if you will, that determine the structure. So it's a very complicated thing that we know a lot, but there's a lot that is difficult to understand in there as well.
Yeah. Okay. Let's. Alan, did you get your mic working?
Is it working? Can you hear me?
Yes. What's up, my friend?
All right.
You have a question for us?
This whole discussion has to do with classical space-time. So we've got these observables, and we're measuring the distances and coordinates. What I never can figure out, and bear with me, I'm an enthusiast, not educating this. When you discuss these fluctuations emerging from the quantum field, you'll hear Sean Carroll describe a field that fills all of space. Well, if you have a one-to-one mapping between the quantum field and space-time, you are in a domain of objective geometry, which entails, I think you mentioned growing block universe, which would be versus the block universe. How does it work in that if you want to have a kind of a physicalist view of the quantum field, and you have these, atheist physicists discussing quantum fields that have a one-to-one mapping, aren't they describing space-time as, even in an MWY many worlds interpretation, a branch blocking of universes because they're having to adopt the initial conditions of special relativity? Are we, when we're discussing classicalized space-time with these one-to-one mappings, basically, aren't we always describing creative event spaces that aren't, physically local, because they kind of transcend causality?
So I don't know. I'm gonna have to kind of walk through your.
There's a lot to parse there.
Yeah.
I mean, like,
Sorry.
how'd you go from many worlds hypothesis to growing block universe?
No. In the many worlds, it has to adopt initial conditions of special relativity. So as it's branching, it's doing what's called a plexus model, which is called, I call it branch blocking. So even though you may stay unitary, you are not stepping through states. Each initial additional state produces a block universe. So you don't escape the ex nihilo event space of the adoption by, getting away from collapse that way.
Well, that's some of this is going to, some of the answer to your question is going to play into what is the actual mechanism behind quantum mechanics. And this is the dilemma we have, is that I can take a Copenhagen interpretation, which is you've got this wave function, which is what we do all our calculations on, and I can predict the outcomes from a probabilistic standpoint of any measurement. But that doesn't change the fact that before I make the measurement, the wave function is both in a up and a down state, and I'm only going to get either up or down. And so Copenhagen says the wave function collapses, and that, so if I measure down, that up state disappears and it all becomes down. But you have the
Everett.
Yeah, the Everett interpretation,
right.
Which is, or even some sort of decoherence where there were these two states and they kind of decohere, and now I'm only in this one, which kind of has this block universe type look to it, that there's all this stuff that's out there and we're just kind of navigating some quantum mechanical path through it, but it's all there. And so
isn't somebody like Sean Carroll using this as a way to reinstate determinism, also describing, unfortunately, he's trying to slip in the back door a metaphysically non-theistic nature? But because of block universe, to me, those are creative event spaces. Those are creative spaces. So it seems like
that's fair. And I think you're right. And what I have seen is that when you're dealing with quantum mechanics, you have to give up something, and we don't know what. You either give up causality or locality. I mean, there's different things that different interpretations say, yes, we've got this, but no, we don't have that.
Right.
And there's, so that means there's a block universe as opposed to a causal, all sorts of things play out like that. But what I've to the quantum people, the physicists I know who are well versed in quantum mechanics, I asked them, what do we do with all of these different interpretations that are floating around? And kind of the universal answer is we don't know what the right answer is. We don't know the fundamental reality. Let me just finish there. Which means that, one, I'm not obligated to take any particular viewpoint or any particular interpretation, but it also means that we really don't, at that fundamental level, understand the universe in a fundamental reality. And so, the fact that he likes the one where you get this and you don't it fits more comfortably in there's no God there, doesn't mean that that's right any more than I like this one because it fits more comfortable with what I like and it points to a God. We're kind of battling at something where science really can't decide at this point.
One second, Alan. 1 second. So, Alan, let me ask you, because these seem like more like philosophical questions. I mean, for example, if I wanted to ascribe to like presentism versus like eternalism or something like that, whether I say that only the present exists, or I might metaphysically think that present, future, past all somehow coexist simultaneously with each other, or exist in some kind of, like you said, growing block universe, which I don't understand very well, by the way. I get kind of the concept, but these are just different, Dr. Zweerink was saying that these are kind of just a philosophical approach. There's really no one set way of looking at quantum mechanics because they all seem to kind of work. So whatever base reality is, whatever realism is there, I don't think that we have a way to detect that. Now, in the RTB model, do they even predict that we can ever know what kind of base reality would be, ontologically speaking, if a deity did exist as opposed to a deity not existing? I mean, is there something that they would predict this is what we would expect one way or another?
Yeah, yes, you can. You can, because from the PSR, you have to achieve not just a principle.
I don't accept PSR.
Yeah,
well, no. But hold with me. You have to achieve a sufficient principle. And when you deal with these either non-local causal states or these block event spaces, neither are sufficiently causal.
Okay.
They're non-local, acausal, achronal, atemporal. None of the antecedents are, sufficient as far as saying that's a direct spatiotemporal constituent that is produced a cause.
Well, I agree with that. Well, that's one of the reasons why I disagree with the PSR, because I think there's acausal relationships in certain quantum mechanical effects like weak nuclear decay and spontaneous fission, because I don't accept local hidden variables. But we're trying to dive.
But what you end up with is a damned if you do, damned if you don't. If you want to take the locality, you end up in block. If you want to take the non-locality, you end up in transcendent cause. So both are metaphysically theistic if you want to approach that there is a creative force that is producing space-time. And that's why I'm curious about this one particular claim of the quantum field being a one-to-one mapping, because it seems like you are mapping a fluctuation directly at the same coordinate as the production of the particle. So therefore you are mapping a block state because it is objectively geometric. I get what you're saying as far as them being philosophical, but even in logical positivism, you have things like the terrestrial muon that does flatten the experimenter and his sense organs during detection. You can't simply escape.
How is that logical positive? I know in the muon decay experiments.
Well, in the muon decay, you've got an experimentalist receiving a muon, but in order for him to have done that, he would have had to be flattened by the frame of the muon.
Right. That's why it's like 10 times or 20 times
exactly. A lot sooner. His brain at that point was a 30th its normal volume that we see in our local frame.
Logical positivism only states that something to be cognitively meaningful has to be able to have a truth or false value to it.
Well, I get that, but you also have this concept of what's valuable is what the senses are involved in, and if the senses are being flattened, as in your nasal passages, your eyes, your brain are being flattened, then you kind of end up in what I describe as a metaphenomena, where you want to lean on phenomenal, but even in order to get to your phenomenally experiment you just told you've been flattened in the process.
I think we're going to put that on hold until I get a philosopher in here.
Nah, but can I before I go, because I got to.
Sure. By the way, can I ask what is your background? I've known you for a while, but I never really asked what your background. I know it's in science, but
I'm an artist, and I just for
a lot of this stuff. Okay.
Just for goofs, I listen to lectures while I work, and I did attend seminary many years ago, which I did not enjoy.
Okay,
so that's my background.
All right, did you want to wrap it up?
So I guess before I go, I'm curious if this one-to-one mapping of the quantum field to its fluctuating constituent and spatial, this is your coordinate. Does that require block time? Is there a way to get away from this? Result.
I'm going to have to beg ignorance there. I just haven't looked at that. I have not looked at quantum mechanics.
I saw it. Okay.
I tell you what I'm going to do for you, Alan. I actually know a PhD in quantum mechanics is a theoretical physicist that has been talking to me, and she's willing to come on at some point. How about we save that till then?
That'd be fantastic.
Deal?
All right. Awesome.
All right. We also got Dave McGinnis in here, one of the co-producers for the Non Sequitur show, starting up his own show called the Slippery Slope program, dealing with fallacies, which is going to be fascinating because, boy, do we need to talk about fallacies one day again. But, David, you got a question?
Yeah, it's not about quantum physics so much, though.
Good.
That is planetary stuff.
Jeff's like, thank you. He's been praying, please make it about astrophysics.
So I was having an interesting conversation with Landon a while back, and realized that science fiction had led me terribly astray on something that I just assumed was okay, involving like terraforming planets and stuff.
Okay.
So it was explained to me a few months back that in the same way that like if if you have helium in certain like gases, they'll just leak right out of the atmosphere on Earth, right? Apparently, if you look at Mars, the gravity is sufficiently less that oxygen would just leak out even if you were to produce it, right? So
Probably.
the question is, that seems to be what I like. So how could you possibly actually terraform a planet like Mars, assuming you could get some of the other things done to the point where it could maintain and hold off oxygen within the planet?
Well,
so you overproduce, or
for a long-term basis, you're just not going to.
Yeah.
Now, one thing to realize is that the oxygen in our atmosphere has a pretty short residency time, simply because oxygen is a very reactive molecule. So you've got to have something that is producing the oxygen in order to have oxygen in the atmosphere. So that would be the approach you would be taking in terraforming, is not that we're going to produce an atmosphere that can hold oxygen for a long period of time. It's that we're going to produce an atmosphere where there's enough oxygen being produced by the primary producers that the secondary producers could use it. But
so you'd have to just create you'd have to be having quite a bit more oxygen output on the surface than you would here, wouldn't you, to maintain that?
No, because virtually all the oxygen in our atmosphere is produced by the life on our planet. So,
okay.
That would be the kind of general sense of, we are going to produce something, or replicate an environment where there's enough primary producers that are making the oxygen that's out there. But you do raise an interesting question, in that so for oxygen, that's how you do it, because there's oxygen in lots of different things. So it's how do you extract the oxygen from the minerals, from the stuff that's there to make it. But you have that same problem with water. Oxygen is actually molecular weight 32. Water is molecular weight of 18. And so, the Earth is kind of just at that size, given its temperature, that water has a pretty long gravitational residence time. So we don't leak a lot of water out into space. So you do have the problem of producing a sufficiently dense atmosphere. Even if you could produce enough water in the atmosphere, if you had something like the mass of Mars, which is, I think, about 11% that of the Earth, it may be 30, but it's kind of irrelevant how low it is. You're just going to start leaking water much faster into space. And the other thing you have to worry about with the water is that solar radiation will cause the water to separate into hydrogen and oxygen, which the hydrogen will leak off into space. And so that's actually how Venus lost most of its water. So it's not just, can we get an atmosphere? And as much as Total Recall was kind of cool because it put a big atmosphere up there before, the one I'm remembering where Schwarzenegger dies because he asphyxiates. There's other things you have to do to keep it around, or else you're going to consume up the resources in the planet pretty quickly.
Well, I heard somebody suggest that you could just increase the mass of the planet by bombarding it with a whole bunch of stuff, like dragging space rocks and meteorites and asteroids and whatnot. And I was like, I think that wouldn't work. You would need a lot of stuff.
I guess it depends on how large your planet starts, but you have to realize that if you're dragging all those rocks in and landing them there, that mass gets deposited there, but you're also depositing the energy there. And so you can calculate how much energy that is.
Yeah.
And in all likelihood, you're going to liquefy the surface of the planet for quite some time.
That's what I said. It's just
it doesn't do you very good if you don't have any crust to stand on, Dave.
I'm not saying it's not possible, but you raise a good point. It's a rather challenging, and there's a lot that goes into that we tend to gloss over, at least from a science fiction standpoint.
I know we got two other people to get in here real quick. I got a question from the live chat. I don't want to keep it too much going. We only scheduled for about an hour or so. Gleam asked.
That was all I wanted to ask. I thought it was interesting.
It was a very interesting question. I think I already kind of know the answer to this question, but Gleam had asked, can dark energy and dark matter be considered the same concept as the ether, i.e. the background energy of empty space, or 0-point energy?
The dark matter cannot. The dark matter has at least some sort of, or given our best measurements, and I will just say straight off, gravitationally, we can measure dark matter being around. We don't have any direct measurements of it yet, anything other than gravitational interactions so far. I'm hoping to change that. I'm actually working on an experiment where we're looking to figure out what the dark matter is from a particle standpoint.
It exists. We just don't know what it is.
That's the best theory, I would argue. I actually know people who are not crackpots by any stretch who argue that we just don't understand gravity properly, and when you understand gravity properly, you end up with no dark matter, no dark energy. But
Possible.
I'm going to put that as a possible, but certainly not prevailing model of what's out there. But you look at galaxies, and we can measure the amount of dark matter in the galaxies based on the rotation curves. And so there's got to be something that has actual mass there that is, there's got to be some sort of substance. So you cannot have dark matter be kind of like a 0-point energy. Right. Now with the dark energy, that does seem to have this property of or some of the explanations, whether you call it the cosmological constant, the space energy density, that really does have this kind of 0-point energy of space, that if it's a space energy density or the cosmological constant, it's just an aspect that pervades space, or rather where space has 3 dimensions or 10 dimensions, whatever it is, it also has this scalar field associated with it. And so in that sense, space has mass, if you will. And so it does have this kind of idea of a 0-point energy. It might turn out to be something very different from that, but that is a possibility.
I kind of look at it as a negative cosmological constant, or negative density, because I think you look in the equations if you look at the Einstein's field tensor equations, the cosmological constant would be on one side, but the dark energy would actually be the negative equivalent of that, if I thought.
Maybe the universe is just electric.
Just because you got to measure, you got to have the metric of the curvature of space time, and you have to have the mass equal each other out.
Well, what I would say is this: that where they are different is that mass is attractive and will cause the universe to contract,
and the other one's expansive.
Dark energy has the property; it's kind of like an anti-gravity, causes it to expand, and so. Right. From a net energy standpoint, if the idea is that the net energy of our universe is 0, that's kind of a fairly popular idea right now. And if that's true, then all of that has to add together with gravitational fields to give 0 energy. So there are these other things that play into there, but it does kind of effectively work in some of the if it's a cosmological constant, if you will, then it really does have this property of space where there's just a 0-point energy. It's kind of very similar to that.
I find it interesting, before we get to the last 2 people in here, that most of the questions so far have been very secular in nature. They've been very dedicated to just learning the science, which kind of is indicative to me that whether you're a theist or an atheist, agnostic, whatever you are, I think science transcends all those different things. Now, I have an interest in science. I don't really get into the whole, God exists, God does not exist discussions that much as I actually love talking about the sciences. And I think this is very indicative that most of my audience really is more interested in the science. And I think that Dr. Zweerink here has pointed out that even as the RTB model it's really not anything so far that I've seen different than what we'd expect from a secular point of view, from a just standard cosmological point of view. Would you agree?
A qualified yes. I will say that yes. I'm just talking about standard mainstream science here. And part of what I'm interested in is science is just really cool. I mean, this is fun stuff to study. I mean, I've gotten to study black holes and gamma rays and dark matter. I mean, that's just cool stuff to talk
envious.
about.
I'm so envious. You don't even know.
So it's just a lot of fun. There's this aspect where science has been kind of brought into this battle of does God exist or not? Mm-hmm. And I'm not going to say science is neutral, because I think the philosophical foundations of science flow out of a Judeo-Christian worldview more naturally than any other worldview. So I'm not going to say it's neutral, but at the end of the day, I think there's this place we've gotten to where we can say, hey, we can go out, and what science will do is say, it doesn't matter what your idea is. Put your idea out there and let's go see, does it match reality? And to the extent we're going out trying to figure out how reality operates, it doesn't matter whether you're a Christian or a skeptic or an atheist or a Buddhist or whatever. We're all going to be measuring against the same world there. Now, what will change is that as a Christian, I may have different questions about the universe than a Hindu would or as an atheist would. But I don't, you were never going to measure God's existence or not scientifically, because God is an immaterial being and science is largely concerned with how the material world behaves. But we join in going out and saying, okay, let's go test or put out ideas of how the world behaves and let's go see which one's right. That's what science does. And I love that aspect of it, because it does help get rid of the inherent, I don't want to say biases, that's a little bit of a pejorative term, but we have these ways of looking at it, and it kind of helps sort that out and say, okay, how do things really work, regardless of what you want to be true?
No, and I really don't take umbrage with anything you just said. From your perspective, I think that holds true. And I will admit, my dealings with RTB have been very, very positive, because I think they do have, they want to go out and they want to put forth predictions. They want to put forth things that could be tested. Do I think that they're going to succeed on that? Well, I don't. But I think that the fact that they try is more than I see from a lot of other organizations. Let me tell you, I mean, you know that we deal with a lot of younger creationists, and you've had experience with them. They don't have anything to even put forward. I mean, it's failure after failure after failure after failure. So you're one step ahead of them. But anyways, let me get the other two people in here. Tim Skeptic, my friend.
Yes. How are you doing?
Look at this. You got me twice.
Yeah, I got you twice. Can you hear me?
Yes, buddy.
Okay, good deal. Doesn't look like my mouth is moving, and it should be moving, but it's okay right now. You called on me at the exact perfect time, because I'm agnostic, but I'm an ex-Christian. I am a skeptic, and my question that I have actually involves God. So perfect timing on
right in his field or wheelhouse. He's over here.
Almost as if God wanted it to happen, right? So, Dr. Zweerink, thank you very much for being on here and talking to us, to us scientific peons, because we all love science just as much as you do. You just took more of the approach that I wish I would have taken as a younger adult. So thank you very much for your dedication to science. My question is what form of empirical evidence do you think you will ever find for evidence of God? And let me give you three examples that I have, because you just kind of answered it just now, but I think there's a deeper dive that I think what you're saying to me is that we don't have the capability of empirically proving a creator with our current understanding. So I'm saying, looking forward beyond our current understanding, do you think that we'll find that empirical evidence in a relationship with mathematical constants that appear to be unrelated, breaking through the uncertainty of quantum mechanics? Because to me, when I first had the agnostic approach, I always thought to myself, well, with the uncertainty that is presented with quantum mechanics, there's no way God could be right in front of us in some other form that we just don't understand. And the uncertainty is so high that we'll ever be able to see him that we'll just never be able to see him due to the uncertainty. And finally, do you think maybe breaking through the barriers that general relativity puts up, beyond, like being able to go beyond Planck's units of length to see what's actually happening at the distances we currently just have no concept of measuring?
So I guess the way I would say that is, I think there are kind of generic arguments you can make, the cosmological fine-tuning argument, that those are kind of generically, does a God or a creator exist? To me, the way I look at that is, in my theological perspective, unless God reveals himself, I'm not going to know, or I'm not going to know him. And so the two primary ways he reveals himself are through creation and through his scripture. Where I think science has the most promise to find evidence for a creator is to the extent it can validate what scripture says about this universe. Now, that doesn't mean I don't think when we go look at scripture, we're going to find quantum mechanics woven in there. And if we just study scripture, we're going to be able to extract general relativity and quantum mechanics. I don't think that's what the Bible's largely concerned with. But the Bible does make statements about how things that have happened. It makes statement about people who have lived, about civilizations that have existed, about the formation of the planet, about the origin of the universe. And so those, I think, are the places where, as we can go investigate and ask the question, does the Bible accurately describe what we measure when we look at creation? Then to the extent it does that, that gives me confidence to believe what the Bible has to say. Now, I don't think that's the only way we know God, but I think that's the place where science has the most utility or the best opportunity to provide evidence for a creator. And it's specifically the God of the Bible, not just some generic creator.
Okay. Thank you for your time.
All right. Last but not least, we got Ben. I didn't mean to leave you so long in the waiting room there, Ben. I didn't know that it was for you. I just saw the name Ben. I was like, who is this? But now I know. So what do you got for us?
Well, can you hear me all right, first of all?
I can.
Cool. I kind of wanted to go back to the multiverse stuff that you were talking about a little bit earlier in the stream, but I also kind of wanted to bridge that into what Skeptic just brought up with like the theology aspect of it, because I'm kind of sit in a weird place because I've been learning a lot from Steve, and I wanted to have this conversation with him a lot just recently about modal logic and specifically modal realism, right?
Okay.
I've kind of learned that like my ontology for what I think reality is about is like very strong into multiverse theory, but also very strong into modal realism, right? So like possible world like conversations and everything are real actual places and such. And I feel like that fits into a multiverse theory pretty well.
He talks about this in this book, actually.
I need to get that book then.
Yeah, I mean, it's not so much modal realism you talk about, Dr. Zweerink, but you actually mention towards the end something along the lines of multiverse being a possible worlds type of thing, where you have a different, like for example, I could be somebody completely different in the multiverse.
Yeah, so there are, and I guess I know what modal means, but I'm trying to figure out what it's a philosophical term that I'm not precisely up on the definition, but there are, when you deal with the multiverse, there's two questions pertinent to my mind as a scientist and a Christian and as an apologist trying to wrestle with that. One is, does the multiverse get rid of a beginning? And I think the answer to that is we still don't know for sure, but not definitively by any stretch. And then there's this other question of, does it explain life, if you will? And what I find interesting is that I think you can make an argument that historically we've looking at how do we explain the kind of the rarity of life. I mean, there's a lot of things that need to be true of life. Life has a high degree of complexity. It's not just your run-of-the-mill thing. And I think there are people who argue, oh, life happens wherever it can. But there are some fine-tuned aspects of the earth and the universe for life to exist. And so one place the multiverse comes in and says, hey, we can explain why there's a place like Earth and a universe like ours that doesn't require any tuning. It's just part of that ensemble of stuff that happens out there. And so it seems to address this longstanding claim of life looks designed. Why, how is it not designed if it looks designed? Yeah. But in the process of doing that, it opens up a different question, because in the multiverse, we no longer can just ask, how do you explain life here? You have to now compare it to all the other kinds of life, because the multiverse effectively says whatever can happen does happen out there. And so if anything can, we have to deal with all the stuff that could happen. And this is where you get into Boltzmann brains. I mean, they may not exist.
You mentioned that in here too, by the way. I don't know. Theoretically, I guess they're possible, but what would happen if a Boltzmann brain did develop? If you might want to explain to people what it is, but
so a Boltzmann brain, so it's predicated on, if you're going to use the multiverse to get rid of God, one thing that has to be true is everything is just purely physical. So our minds are just an arrangement of all the atoms with the right configuration and velocities, if you will. And so they're very highly complex, not far out of equilibrium with the universe, but there's energy out in space, and you can have fluctuations that are very large. And if the multiverse is large enough, you can have incredibly large fluctuations where this thermal fluctuation might bring all of the atoms into a place that replicates a mind. And so you've got this mind that comes into existence and says, oh, I'm here, and then poofs out of existence.
Yeah, it literally happens like that. If theory, if a Boltzmann brain was to exist, it would exist for just a very, 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 very short period of time, right?
Well, that's the most likely form. But you can have Boltzmann brains that are fluctuated, that have a longer history, or see a very ordered universe. You can do it's just a bigger fluctuation.
It's too bizarre.
They're just more rare. And so the ones that you would expect are just those very brief temporal ones. And so this is the question that now that arises, and you got different people have different takes on this. Sean Carroll says no, Boltzmann brains can't exist; they're cognitively unstable. But that doesn't really address physically is it possible. And so these are the sorts of questions you have to wrestle with.
Yeah, and well, Ben brought up modal realism versus like modal anti-realism. What he's referring to is if something is logically possible, that means it must exist in some possible world. If it's something that's metaphysically necessity, like God would be, most theists would posit that God is a metaphysical necessity, which means that it would have to be logically the case that it is all possible worlds, right? God would have to exist in all possible worlds. And if something is a logical impossibility, it cannot exist in any. The modal realist says that these are actual ontological worlds out there that have ontology to it. The modal anti-realist, which would be me, says that they do not have ontology, but I recognize that these possible worlds are possible worlds. That's the device said, if it is logically possible for this deity to exist, it must exist on some possible world. But that doesn't mean that it actually has ontology. Ben, is that your question, by the way, to me?
Yeah, more or less. So I think part of the reason is that throwing around these like multiverse term links, like that picture that you showed earlier with like
it's very similar to this,
things,
right?
Yeah, that's really cool, right? But I also, so I'm a big science fiction nerd. I know about like parallel timelines and like Back to the Future is how it go back and it folds in on itself and all that garbage, right? Yeah. So like when you're looking at like timeline stuff and you're looking at universes stuff and you're looking at multiple universe stuff, but then you also throw in the abstraction of like possible worlds,
right?
Like when JFK wasn't assassinated or something.
It bloats your ontology, though. It's so confusing when you're dealing with counterfactuals.
But here's the thing, though, is that like I feel like there needs to be some distinction posited when you're talking about an individual universe's timeline and the counterfactuals that exist for it.
They're two different things,
right? Right. No,
yeah.
So you can have multiple. So I can have two universes, right? And let's say one universe had JFK, or both universes had JFK, right?
Mm-hmm.
One JFK died, one JFK didn't. But is this one universe the counterfactual to the other one, and vice versa, or are there counterfactuals amongst those individual universes for like an abstract kind of sense? And when you're talking about realism, like modal realism, for that, does the multiverse simply reflect the abstract like counterfactuals per universe, or does it represent the actuality of the multiverse around it, right? So it gets super confusing. But
so I can tell you how how I think about it, and I think that reflects largely how most scientists think about it. I mean, you can go talk among scientists, and there's this argument as to whether the multiverse is good for science or not, because you do kind of end up with this everything that could happen does happen type thing.
Mm-hmm.
And I think if you push that far enough, you really undermine the very basis of science, and so I think there's some problems philosophically or whatever. But the way it's thought about, or it's articulated most often, is that whatever is possible actually happens out there. Now, we have to realize that we don't always know what is or isn't possible. So we could, in your scenario about JFK there, we could think, oh, hey, it's possible that JFK didn't actually get shot, or that he got shot and lived. The reality could be that physics constrains things so that there was no way he wasn't going to get shot and killed. And so in the multiverse would say all of the possibilities of what could have happened actually did happen somewhere, because it's just a variant on the initial conditions. They're all traced back to the initial conditions, and every possible set of initial conditions is realized. What we're now arguing about is how large is that space? And with JFK getting shot, we can imagine a lot of different things. But one place where this is where it does come to play, where we don't have the answer is, we talk about the laws of physics being fine-tuned. If the speed of light was a little bit larger, a little bit less, than whatever. The reality of it is we have no idea what the speed of light could be. It could be the only value possible is 3.00 times 10 to the 10 meters per second, or 10 to the 8 meters per second. Or it could be that it could vary between 2 and 4 by discrete values, or it could have any rate. There's nothing in our physics that constrains that at this point. Now, we might find that in the future, although I kind of doubtful we'll find that. Typically, where we've gotten a more general theory, the range of possibilities is increased, not decreased.
Yeah.
But so the physicist or the cosmologist who says the multiverse is an actual existence out there will say every set of possible conditions has realized itself somewhere in the multiverse. The best we can do is talk about which happens. We could talk about the ratio. So it may be that things end up at the bottom of the hill 10 times more than the top of the hill.
Yeah.
But we don't know. We can't say anything more than that. That's kind of the scenario you end up in. And so I think that aspect, if you push it too hard, is going to be problematic for science. And that's part of why I think, as a theist, I don't have to worry about a lot of those things, because the only place where Jeff Zweerink exists is where God created Jeff Zweerink. So you can get all those things out there in the multiverse, but all I have to really worry about is what he did here. That's my take on it.
So these subjunctive cases, the counterfactual cases, there would be some kind of ontology in the multiverse, because in the possible world semantics, they don't have ontology unless you're a realist. But if you look real quickly at the multiverse, because I didn't show this earlier, maybe I should have. This is a level 1 multiverse. These are Hubble spheres, right? So we're at the very center of one of them, and that everything outside of our sphere is forever out of our dominion. We can never have any causal relationship between them. The level 2 would be basically these little nucleation universes, right? And then level 3 would be, it looks kind of like multi-worlds approach.
It's quantum mechanical multiverse.
Okay, so and then this is 4. Forget this. I
love 4. No. Give me 4 every day.
All level 4 says is that we've got this set of mathematics we use to do all of this, but there are other ways we can see mathematics works. And it's just saying that those if there's a mathematics that describes it, there are universes that exhibit those mathematical structures.
But isn't that more like a mathematical Platonism type thing?
Yes.
Okay. Yeah. Fair enough. And by the way, a lot of mathematicians do subscribe to mathematical Platonism. I get why, but
if you want to find somebody who argues for that, and I think articulates it fairly well, Max Tegmark takes that sort of view.
Yeah.
Mathematics defines reality. Yeah. Mathematics determines matter, determines mind. So is the way you would say it.
There is an interesting attempt by Max Tegmark of saying basically the level 1 multiverse and the level 3 multiverse are indistinguishable. If you say one exists and the other exists, how do you determine that you are in a level 1 multiverse or level 3 multiverse if what you measure is the same?
I think it's the level 2 and the level 3 are indistinguishable, because the level 1 is just a whole bunch more of the same stuff. But when you look at the difference between the level 2 and the level 3 is the mechanism that produces it. The level 2 is an inflationary multiverse that realizes all the conditions. The level 3 is a quantum mechanical multiverse that realizes all the conditions. So if you were to take a snapshot at any given time, they would look different. But statistically, from a bird's eye view, they're going to be identical.
That makes a lot more sense, because the level 1 to me just seems like it's bounded by the conditions of light speed.
Exactly. It's the size of the universe, or the age of the universe, and the speed of light determine the size of the multiverse, or the size of our Hubble volumes.
Makes a lot more sense. I'm going to have 2. Go ahead, Tom. Then I got to read 2 super chats and we got to wrap.
Go ahead. With
okay.
Super chats.
Super chats. Oshkosh begot Josh. Are there any well-known universities in Midwestern America that have a good astrophysics program?
Yes. I mean, you've got the University of Chicago would have one. I would say Iowa State has a good astrophysics program.
Yes,
the University of Missouri does. I mean, I'm just thinking of ones that I've had direct experience with. But yeah, there's a lot of good universities that have good astrophysics program. What I would encourage you, I mean, if you're looking into that, is, find a good undergraduate program, but then find the program that works in the area you want to work in. So if you wanted to do high energy gamma ray astrophysics, you would not go to the University of Missouri because they don't have anybody who works in high energy astrophysics. But you could go to Iowa State because they got people there. You go to the University of Chicago because they got people there. So that the undergraduate program is more how good is the program for a general degree. But then when you go to graduate school, you want to look into, are they studying the things that you're interested in studying?
I will say S&T, the University of Missouri, that's where I graduated from, but they have a very good laser physics program, if I recall correctly.
Which one is that?
It's the University of Missouri of Science and Technology. It used to be a UMR.
Oh yeah, that's actually where my dad graduated. So
I'm gonna try. Landon Kurtnell actually is friends with Dr. Suskind, and I'm gonna still trying to get Dr. Suskind to come on. That would be amazing because I want to talk about the cosmic landscape, which I have here. Only got halfway through it, but I'll finish. And I also, Ben, you might be interested. I have reached out to Dr. Graham Priest. Do you know who he is?
Graham Priest.
Dr. Graham Priest is he probably is the leading expert on modal logic.
Yeah, you told me about it. That's the show that you said was going to happen months ago.
No, it's supposed to happen in April.
April. Okay,
so
yeah,
we're not that far off.
Dude,
so.
Absolutely, let me know about that.
Yeah, so I'm gonna get back in touch with
I want to get a little bit deeper into the modal logic stuff because I really want to talk to you about level 4, and I think I can convince you maybe.
Sure.
Me or him?
I don't know. Not me. I mean, maybe him.
If you want to come on.
I think we can probably get a mathematician into that one as well. Sarah Beer asks, he says, somehow it's believed we know the universe is infinite. We know, quote, the universe is expanding. If the universe is expanding and infinite, what is the name of the space not occupied by the universe? Math? I think he's asking like, what is it expanding into?
Well, so I would make two statements to that. One is that we know the universe is expanding. That's a pretty non-disputable statement in our universe.
Yeah.
We do not know the actual size of the universe. Now, most cosmologists will say our Hubble or our bubble universe is spatially infinite, but all we know is the minimum size. We don't know how large it is. And that's true whether it's infinite or not. There's this question of what is it expanding into. And the short answer is it's not expanding into anything, because the only thing that exists is the space-time fabric, space-time matter and energy of the universe or the multiverse. And so it's just something that is growing larger. It's not expanding into anything, because if it were expanding into anything, that anything would be part of our universe.
Mm-hmm.
And it's just growing larger.
There's a good term that I stumbled across at one point that I like. It's called the xenoverse, right?
Okay.
It's from xeno, like xenomorph or something from like Alien. It's the alienness that we just can't even understand out there.
Okay, so it's X, not a Z. Then.
I would look at that more.
X.
If you look at like a Minkowski diagram, you have a region of space past the 45 degree light cone, right? So you have a light cone from any particular point that's going out. So anything that light cone is never going to actually reach, that's going to be outside of our observation. It's anything outside of that particular light cone from our particular observation, that light could never reach us, right? Mm-hmm. That whatever space is expanding, it's not really expanding in anything. It's actually creating its own volume.
Well, so I often use that balloon analogy, because that's what, how do things expand? What does that look like? You can draw dots on a balloon. When you blow the balloon up, you say, oh, that's clearly, it's expanding into this other space. But that's because we're three-dimensional beings looking at a two-dimensional analogy, if you will. If you are a two-dimensional being confined to the surface of that balloon, all you would know is that the amount of space you had was growing larger. There is no up or down. You can't say you're expanding into anything or not. Now, maybe God's out there looking and knowing what it's expanding into, but to our knowledge, there's only the space-time fabric of this universe and the multiverse. So you can't say, oh, it's expanding into this, because there is no this for it to expand into that we have any sort of knowledge of.
Yeah, I would recommend to the people watching, go read a book called Flatland.
Yes. That is a great book.
So that would kind of, because these are
very enough written by a journalist. He's somebody without a math background. Yeah,
Abbott wrote it.
Right.
But these are very ineffable concepts, right? I mean, they're very hard to put into words. And so I'm grateful that we have people like you that come into these shows and actually describe these things in a way that I think the average schmuckatelli like us can understand, because I'm a layperson. I've taken physics courses and I have a small background in physics. It's nothing comparable to the people that I have on the channel. So when I'm having an opportunity to have a discussion with somebody like yourself, I'm thrilled to death. And if I'm happy, my audience is happy. My audience is happy. I'm happy. See how that works? But I'm going to wrap this up. I want to thank everybody for watching this. I am going to be trying to get some more people from RTB. I think that we have some of the greatest discussions with them. We've had obviously Fuzz Rana on and Dr. Ross, just brilliant guests. There's a couple others that I'm hoping to reach out to. But Dr. Zweerink, I want to thank you very much for coming on. If there's anything you want to leave us with RTB, promote anything, happy to promote your book. go around and get this book. Because, by the way, if you haven't ever read anything on the multiverse, if this doesn't explain it to you, nothing will, because he breaks it down very easily to read. I got to admit, even though the level 4 I don't get, but that's just not your fault.
I appreciate the kind comments there. And, I would say, one thing that I've just finished writing and that is supposed to come out in September is a book on, does science say the universe has a beginning or not? And so the book is called Escaping the Beginning. But this is one of those areas where I think we're in an area where science, or at least quantum mechanics, there's ideas out there that say, oh, there's no beginning, and we're kind of getting rid of that. But I think you can make a strong historical case that the universe seems to keep pushing us back to a beginning. And I think that's very consistent with what Christianity has to say. And so I would encourage you to, if those sorts of things, kind of hopefully along with what you're saying there, it's understandable. This is not for the technically minded, although I think it will be accurate to the technically minded, but it really is to help people understand what's some of the science that's gone out there and how do I think about that well. So.
Yeah, these are, like I said, these are not easy subjects. We recognize that, but the fact that we have such an eclectic group of people coming in from such a diverse background that can describe these things, I mean, I'm just thrilled to death. And the fact that, to me, like I said, I don't really care if somebody's a theist or an atheist or agnostic or whatever. I'm into the science, but if they can relate it from their particular worldview, even better, right? And maybe next time we have you on, if you ever decide to come back, if you're not too scared off, we'll have more of a conversation between somebody who has like a physics background but more of an atheistic worldview, and then you can compare the RTB worldview. I'd find that to be pretty fascinating. Sound good?
I think that would be a great discussion.
All right, and I want to thank again Anastasia for arranging this. I don't know if she's watching, but she's the, I guess, publicity person. Publicist for RTB, and she does an amazing job. So I want to thank her if she's watching or ever does watch this. But with that, I'm gonna leave you guys. Don't forget to watch Non Sequitur Show tonight. We've got climate change on tonight. Not exactly sure what they're coming on to talk about on climate change. Good, bad, or indifferent. We'll find out. To me, climate change is real, but maybe they can try to convince me otherwise. They won't. Good night.